Okay. Wait. Do you see whiteboard? Okay. Do you see whiteboard? Do you see whiteboard? Do you see whiteboard? Answer me. Yes or no? Hello, hello, hello. Answer me. Do you see whiteboard? Guys, do you see whiteboard? Let me see. Yes. Ricardo is a yes. Okay. Are you ready to pay attention? Are you ready? Are you ready to pay attention? Answer me. Come on. Fiddy, Daniela, Giraldo, Ricardo. Okay. And Marco. No? Marco. That's it. Wow. Okay. So today, do you see que I sent in the email the study guide for the test 4, right? The review package, no? Do you see or no? I suppose we start doing next week. Okay, next week we dedicate 2 lectures or 3 lectures because it's complicated. Okay, now entonces ready, no? Daniela Rabasa is coming now. No, it's left. Wow. No, it's joined. Okay. Okay, now ready. I bring today 2 problems of the surface area. Surface area, compute the surface area of the one specific surface is given. This problem I want to do in different way. I do in implicit formulas, explicit formulas, and parametric. Okay, I have another problem similar, a little bit more complicated. And after that, we compute some surface integral. Because remember, surface area is one specific case of the surface integral in which the integral function is 1, no? Okay. Ready. Entonces, for example, I suppose that you know very well what kind of surface it is. What kind? What is the graph of this? This is not strictly necessary to do that. However, I want to practice a little bit, no? What kind of surface it is? I need to first name, last name of this surface. Okay, my objective is find the surface area of this that represent this equation above the xy plane. So in other words, C0. So C greater than or equal to 0. This is equivalent to say C greater than or equal to 0. What kind? Come on, what kind of surface it is? So you finish calculus 3 and you never remember surface. Yes or no? No, never remember surface. Robin, Daniela, Omar, okay. What kind? No idea. Only Gerardo is the only student can answer me always. Gerardo, you don't know the surface? Well, let me try to put in maybe explicit form. So you solve for C. So C is equal 1 minus x squared minus x y squared. So you solve for C, que you know que C is equivalent to say fx comma y, no? This is totally explicit form. And this will look like a little bit like implicit. Well, implicit you know que es fx comma y comma z equal to 0. Entonces, no, si you want, que no exactly mandatory, equal constant. Okay, but it's okay. C equal to 0. Entonces you rewrite in that way, no? Es C plus x squared plus y squared minus 1 equals 0. Okay, this is implicit. 4. And this is explicit form. Now, entonces my question was no answer. What kind? What kind? Look at this. Okay, you are a little bit familiar with this. What kind? Guys, are you sleeping or you are paying attention? David, what kind of surface? We need to compute the surface area. Robin, Daniela, Omar, answer me. Carlos Duque, okay, Carlos Duque. Giraldo, you don't know, you know. Hello. Ajá. Paraboloide. Giraldo, definitely. Remember surface, paraboloide, pero paraboloide along what axis? Along what axis? Z-axis, very well. And what direction open? And what direction open? Open up or open down? And what direction open? Open up or open down? Open up, I believe. No, Giraldo, because it's negative. Look. Okay, so you are doing the trace of this surface. You have parabolas que open down because it's negative. Okay, entonces our parabola look like that. Look, we have the intersecting here, que es the point 0,0,1. Or in the x is 0, y is 0, z is 1. Open, down, like that. And stop. I see now. Okay, Carlos Duque. Okay, and open down. See, open down. Okay, and this is our surface. Not only the positive parts, it's completely around the CX. So this is the thing I want to determine. Okay. So your identification. So first of all, let's use the implicit. Doesn't matter the order. I want to do it in a different way. Implicit, explicit, and parameterization. And you see it's the same. And you go in the test you are doing it only one way, the way you prefer. And sometimes happen that one way is hard, complicated. Complicated the integral part or the algebra part. Okay, suppose implicit. Entonces now in implicit the formula, you compute the gradient of capital F. And the gradient capital F, you differentiate partial derivative of this expression. With respect to x, x to x. Comma, with respect to y, x to y. With respect to z, f1. Do you understand this or no? Partial derivative of the implicit formula. All good. Okay, I find the magnitude. This guy. The magnitude is square root 4x squared plus 4y squared plus 1. Entonces in this case is above the xy plane. Entonces when it's xy plane, you perform the dot product, this vector, the magnitude, this dot product k, because it's on the xy plane. Okay, now in this case it's obvious that this is equal 1, because when you perform the dot product, remember k vector is a vector 0,0,1. When you are doing this dot product and this vector, 0 times 2x is 0 plus 0 times 2y is 0, and 1 times 1 is 1. Okay, super. Now the formula say division. The formula say ds. The infinitesimal, elementary surface area is the division magnitude of F divided by, it's a formula, magnitude of gradient dot K, no? Okay, by the way, this guy is 1, and the answer is ds is equal, that part is square root 4x squared plus, well, here is dA, sorry, 4y squared plus 1. In this case, dA is specific at dx dy because the projection was over the xy plane. How do you know? Because you're using the unit vector k, que es the perpendicular unit vector to this plane. Okay. The rest is the integration. So this surface integral is equal to the double integral of this integrand function in the region R. And who is the region R? Well, the region R is the projection of this yellow surface on the XY plane. Que entonces, si I am doing the sketch in 2D, look, we have a circle, no? That circle, que es this circle. That circle. By the way, see, I suppose que Z is 0 on the XY plane. I come back to the original formula. Look at that, the original formula under the supposition que Z is 0 is x squared plus y squared equal 1. And to say this, we have a circle with the radius 1. Okay, entonces my goal now is set up the double integral and this. Es obvio que the easy way is using polar coordinate. Entonces now I can modification this integral que somebody not me, I set out in Cartesian xy in polar. This is my region R. Look, this R region is this R region. And this S is this surface. Do you see how we transform it? We use the formula, no? Okay, this is polar is, you know, for a common factor here in this expression. I need to modification a little bit the integral function for its common factor. So we have x squared plus y squared is r squared plus 1. Actually is a square root my integrand function r squared plus 1. Remember the Jacobian. The Jacobian is r dr d theta. And the limit is r vary from 0 to 1. Look at that. Unit circle. And theta vary from 0 to 1. The rest is cal 1. Oh no, cal 1 because it's easy because you can separate. But I don't want to waste the time. It's the most important thing to discuss in today. The answer is 5. Radical 5 minus 1 over 6 pi. It's the answer. This is one way to do this problem. This is one way to do this problem. Any question? Any question? What part is confusing? Come on. I use it because I have no idea the implicit form. Because I suppose I understand much better when the professor explained that part. No. Let's do it in explicit and let's do it, why not, in parameterization. To see the big picture for this. Any question, guys? Come on. I want to hear opinions. Victoria, Carlo, David, clear. Okay, clear. Okay. Okay. Suppose. No, professor, I don't like this. I want to do it a different way. You explain me que, for example, si yo isolate C, que C is 1 minus x squared minus y squared, and you assume que C is f of x, comma y, is 1 minus x squared minus y squared. And this is explicit. Explicit is when the C, 4, when the C is isolated, and you call F, little f, no capital F, little f. Entonces the formula for the explicit is something like that. ds is a square root of the f of x squared plus f of y squared plus 1 dx dy. There are different formulas, no? Depending the projections. You're projecting onto the xy plane, or you're projecting another plane, but in this case xy plane, no? Because the problem talking about the surface is above the xy plane. Entonces now you differentiate. What is the fx? Differentiation, this expression, this one, with respect to x, is minus 2x. And differentiation with respect to y is minus 2y. I'm plugging in here in the formula. The formula say square root. I square this, and see if negative become positive, is 4x squared plus 4y squared plus 1 dxy. And you can see, I don't want to do again, it's exactly the same formula that we have in this moment. Okay, now your integration, both sides, you convert the surface integral and double integral. And the same region, the region is, in this case, the shadow of the surface, the yellow surface, onto the xy plane is a circle, unit circle, no? I don't want to repeat again because it's the same thing. And definitely you finish the integration in polar, no? Because it's more comfortable. Any question? Wow, it's really easy. It's really easy. Explicit. Entonces dependen, guys, the problem. Sometimes it's easy explicit, sometimes it's easy implicit, or sometimes it's easy parametrization. When you have maybe complicated surface, it's much better parametrization. Let's do it using parametrization. Parametrization now. And my goal in the parametrization is, look, I copy again. That equation, okay, the equation. We start always for the surface equation. 1 minus x squared minus y squared. Well. So that part look like familiar. X squared plus y squared. Parametrization is a circle. That part is a circle. So you call, for example, x is equal r cosine theta, y is equal r sine theta. And at least I know that x squared plus y squared addition is 1, no? That part. And C, bueno, C is 1 minus something, 1 minus x squared minus y squared. But I know that if you factorization, for example, this negative 1 outside, we have x squared plus y squared, no? And x squared plus y squared is r squared. Now remember, the parametrization, one surface need 2 parameters. In this case, normally we call in general a U and B, but no. In this case, I want to call, for example, this is the vector value function that depends on the two things, r and theta. And the parametrization is x, the function x is r cosine theta, the function y is r sine theta, and the function z is 1 minus r squared. Do not depend on theta. Entonces now the domain of this, by the way, the domain is the region, no? Que you change like a double integral. The domain of this region is theta vary. This is theta and this is r. It's completely different plane, no? The traditional xy plane. No, it's the r theta plane. Theta vary from 0 to pi. Because I know that my surface is totally cylindrical. No, not exactly cylindrical, it's paraboloid, no? And r vary from 0 to 1. This is my domain of the parameterization. Okay, by the way, rectangle. I like this because it's easy the integration. Okay. So you put together, attach the parameterization and this idea. Theta vary from 0 to pi, and r vary from 0 to 1. In our specific example. Okay, now ready. Entonces now the formula is you compute RR. So you compute the partial derivative of this vector value function with respect to R. Entonces es cosine theta, coma, sin theta, coma, minus 2R. Okay, I differentiate with respect to R, derivative R is 1. You consider the cosine theta is constant. And the second component exactly the same. And the last component, no, is not dependent on theta. Derivative 1 is 0. Derivative minus 2R is 2R. The R squared, sorry, is negative 1. Likewise, derivative, partial derivative with respect to theta is, well, derivative this is minus R sine, because now I differentiate with respect to theta. The cosine is minus sine, and R I consider it constant. Derivative sine is cosine, and derivative, the last part with respect to theta is 0 because do not depend on theta. Now you perform the cross product. It's the same idea always. It's I, jk. The first vector is cosine theta, sine theta, and minus 2r. The second vector is minus r sine theta, r cosine theta, and 0. And you are doing this cross product. I don't want to do, I only put the final answer. The final answer is minus 2r squared cosine theta, comma, minus 2r squared sine theta, comma, r. Okay, now I compute the magnitude of this. Magnitude is the square root of the sum of the component one by one. You square this guy. We have 4 R4 cosine square theta. When you square the second, it's 4 R to the 4 sine square theta plus R square. It's obvious that you factor out 4 R4 power. You have sine, cosine square plus sine square is 1. So the answer so far is square root 4R to the 4 power plus R2. Good. Now your factorization, the common factor is R squared. So far the magnitude of this is, okay, you factor out, okay, basically in my mind, this is like a R squared is common factor, parenthesis 4R squared plus 1, right? To the square root this guy, this is only R, square root 4R squared plus 1. Okay, now in order to find the surface area, the ds is this guy. dr detail. Entonces you integration here, and this integral, double integral is double integral, not surface integral. And entonces who is the region R? The region R is different now. The region R is this region, que es rectangular. Now look, it's different to this. In this case, it's not rectangular. This is a circle, unit circle. Now I replace. This is double integral. The integral function is 4r squared plus 1, and we have extra r. Entonces dr detail, ¿no? But in this case, look, pay attention. Notice. We are doing different. We are doing no transformation polar. Aromática was polar, pero no. Was parametrization. Entonces no necesariamente Jacobian, es dr detail. Pero this r is exactly the Jacobian que you see in the last method, no? In the first implicit or explicit. Automatically appear suddenly, magically. No, it's a mathematical, not magic. They are. And the limit of the integral is the same, 0 to pi, theta, and 0 to 1. Wow, fantastic. And of course, the same integral, and you expect the same answer. Beautiful. Any question? But notice, in this way, when you transform the surface integral to the double integral, no necessarily Jacobian to convert to polar because the domain is rectangular. Okay? Any questions? Super clear or super confusing? Of course, we have to practice, no? Entonces, now in the review packet, you see not too much example, but some example of this. Any question? I need to hear opinions about this. Brandon Thomas. Okay. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 students. Okay. It's a world record in this class. The parameterization was complicated. Okay. I understand. Here I do say that the parameterization is a little bit more complicated in this example. Okay, I understand. Compared to another method. However, sometimes it's the only fantastic option that we have, depending on it. Let me try another example. Example 2. About surface area. Another surface area. In this case is find the surface area of the, okay, we have find the surface area. Find surface area of the surface formed by a sphere x squared plus y squared plus c squared equal to, it's a sphere, right? A sphere with the center is located in the origin, 0,000 center. And the radius is radical 2. And bounded by the plane c equal 1. Let me try to understand this. Okay, remember the geometry interpretation is important because I need to know at least the face of the surface I want to compute, the surface area. Now we have a sphere, 3D picture. We have a sphere radius radical 2. Entonces we have radical 2, radical 2, radical 2, radical 2, radical 2, radical 2. We have radical 2 as a sphere like that. And this distance es obvio que es radical 2. Sphere, roughly sketch. This distance is radical 2. Radical 2. And radical 2. And this is minus radical 2, no? And this is minus radical 2. Sphere. However, we have a plane. The plane is parallel to the xy plane. And the distance is 1. So we have a plane, I don't know exactly like that. And this plane cut out the sphere. I don't know exactly where. Well, in 1 because it's equal 1, no? And radical 2 is bigger than 1, no? Radical 2 is 1.41 something. So we have that surface. Okay, and this height 1, get the plane. And this is my famous surface. I want to compute the surface area. Look like a hat, no? Like that. I want to compute the surface area of this. Do you understand a little bit the surface? Es intersection. Okay, no intersection, sorry. Es inside, o sea, belong to the sphere, but this bounded by the plane is equal 1. If you want to see much better, remember my recommendation always, one 3D picture and one 2D picture, no? For example, one lateral view X or Z. We have a sphere like that. And this distance is radical 2, radical 2, radical 2. And we have a plane in 1. And we have a plane in 1. Let me use another color. We have a plane in 1 here. And this is my surface. Look at that. No. Curvy. More clear in this lateral view 2D. More clear. More clear or no? Do you see the surface que we need to compute the surface? Okay, Victoria is yes. Okay, now I propose, I need to make decision using the implicit formula. The implicit formula is, you know, capital F, x comma y comma z is equal x squared plus y squared plus z squared minus 2 equal to 0. I take the sphere part, because important part. So basically, my surface is a piece of the sphere. So this is most important. No, I don't take C equal 1. No, I take the sphere. The majority of the majority, not all, the surface is a sphere. And we computed the gradient. And the gradient is partial derivative capital F. So the gradient is capital F, comma capital Y, capital F, Y. So partial derivative with respect to the X, partial derivative implicit equation with respect to Y, and partial derivative implicit equation with respect to Z. This is the formula, no, of the gradient. In our specific example, you differentiate is 2x is with respect to x, to y, and to z. Wow, easy. And immediately you compute the magnitude of this vector. And the magnitude of this vector is a square root. Square root what? Square root 4x squared plus 4y squared. No, you square this guy, this square this guy, 4c squared. And 4 is common factor. I factor out 4 inside the square root and outside represent 2, no? And stay alive. X squared plus y squared plus c squared, no? Pero I know very well que x squared plus y squared plus c squared is equal to in our problem, in the sphere. Therefore, you replace numerically, because in any point of the sphere, this is equal radical 2. Entonces the answer is 2 radical 2. Wow, amazing. The magnitude is constant. This is good, because simplify a lot of the double integral. Do you follow me? And remember the formula. The formula say you divide this guy and the gradient component K magnitude. Because we are doing on the X, say you projecting onto the XY plane. How do you know? Well, it's the most common projection, no? But however, we can project in other plane using J or I. Entonces, in this case, is the dot product between this vector and the famous K vector, que es 0, 0, 1. And the dot product and multiplication component by component and sum is 0 plus 0 plus 2c. Is this part. It's the component in K. And finally, you divide. You divide what? You divide the magnitude gradient divided by magnitude of this dot product. Actually, this is 2 radical 2, and this is 2c. Entonces, this 2 is cancelled. It's radical 2 over c. And this is the integral function that I plug in. So surface area is equal double integral in the region R. Okay, I have no idea who is the region R so far, but I know that the integral function is radical 2 c dA. So you transform the surface area in one double integral. Well, I need to determine the region R. Well, suppose that the region R, I need to do another sketch in 2D. Okay, we have X and Y axis. Entonces, when you projecting this onto XY axis, I suppose that we have another circle, no? But a small circle. That one. This is as z equals 0. C equals 0, no. C equals 1. So si yo assume que C is 1, que is the plane, C equals 1. We have x squared plus y squared plus 1 squared, que es 1, 2, equal to. Then we have x squared plus y squared equal to minus 1, is 1. Wow, it's again unit circle. So our region R is a unit circle. This is our region R. Entonces easy. At least for me it's easy because I use in polar, no? I use in polar, definitely polar. Entonces es, bueno, radical 2 is a constant. Radical 2 is a constant. Double integral. I need to express z. Bueno, c, remember the formula, the beginning is x squared plus y squared plus c squared equal to. Now DC is DC. I solve for c. Entonces es c squared is equal to minus x squared minus y squared, no? And c alone is square root. 2 minus, is, you know, this is r squared in polar, because remember the decision was applied polar to integration this. So my integral function is, you know, in the denominator c is square root 2 minus r squared. And the top, the top we have radical 2, but I put outside. Therefore, I put the Jacobian. This is r dr dθ. And R go, and the region R from 0 to 1 is the radio, and theta go from 0 to pi because it's a full circle, no quarter circle or semicircle, no. And this is the integral I need to find, and the answer is 2 pi, parenthesis 2 minus radical 2. Okay, look like easy, eh? In that way, no? Any question? I want to do user parameterization. And you see it's a little bit more complicated. Everyone follow me in the second problem? Do you understand or no? So we are doing computation surface area. Entonces I transform it, follow me. I transform it using that formula. I transform it the surface area, que es the surface integral when the integrand function is 1, to the double integral. Okay, let's do exactly the same problem, pero en parametrización. Entonces, es obvio que es a circle. Sorry, es sphere. So my surface is a piece of the sphere. Therefore, the best way to parametrization is using spherical coordinate. In spherical coordinate, I know que x is equal to the radio, que el radio es constant, es radical 2, sine phi, cosine theta. This is the formula for the conversion from spherical coordinate to Cartesian x, y, z. You don't need to memorize this. You taking. Well, when you practice a lot of, you memorize maybe. Sine theta and c is equal to radical 2 cosine phi. This is the range. The interval of phi is from 0 to I don't know. And theta I know. It's 0 to pi because it's completely circle, no? Around. Theta is 2 pi. But to determine phi, well, I come back to this view and to the look. I need to find this angle. Remember, phi is this angle. Look, that angle. Phi. Actually, if we go from 0, que es this, the z-axis, to this value, and this is my surface, and this is look, see this guy 1, and this hypotenuse is radical 2 because it's a radio. Es obvio que the angle is pi over 4, no? This is the classical triangle 1, 1 radical 2, no? This is the pi over 4. Okay, we discover geometrically que phi vary and pi over 4. And this combination of the equation and this represent the piece of the sphere that we have. Okay, guys, this is the beauty of the parameterization. Okay, you can do magic. Now you represent like a vector value function. Vector value function is R. Es phi theta. Oh, in spherical coordinate, the parameter is always angle. Phi and theta is radical 2 sine phi cosine theta, comma radical 2 sine phi sine theta, comma, last comma, radical 2 cosine phi. And this is my domain. Okay, I can represent graphically like that. This is theta and this is phi. From 0 to pi. From 0 to pi over 4. This is my domain in which I finish my double integral. Okay. What should I do now? Well, partial derivative. partial derivative of the vector value function with respect the phi. Partial derivative with respect. I want to do quickly, guys, because it's long. With respect the theta, and you perform the cross product. I did that in my calculator, of course, and the answer is the magnitude of this is 2 sine phi. Okay, finally, you set out the double integral. This is too long process, you know. Too long process. Too long. Okay. Entonces now my double integral is double integral. The integral function is 2 sine phi. And this is the phi, the theta, no? And not Jacobian, because I suppose we are doing the setup of the one double integral in the phi theta plane here in that region. So we don't change variable xy to the circle to the polar. No. And this phi vary from 0 to pi by 4, and theta go from 0 to pi. Bang, we get the same answer. Okay. I know it's hard, but it's systematic. Okay, this the most complicated part, in my opinion, is you need to be familiar with the new idea for the parametrization surface, no? Si es piece of the sphere, it's obvious that we use a spherical coordinate. I proved last class. Okay. Any question? Any question? Okay, then I bring some example now. So this example that we're doing so far is surface area in which the integral function is 1. But no. I want to compute now surface integral, of course, scalar surface integral. I promise that today we start doing vectorial surface integral. Pero no, so far it's scalar. It's scalar. Suppose one example. Example 1 of the scalar surface integral. It computes this surface integral and who is S? So always the integral function is given, okay, maybe have 3 variables x, y, z. This capital S represents the infinitesimal element of the surface area. And the surface is given by this equation. Is equal 1 plus 2x plus 3y, and this is lie above one region is determined by 0,3 cross product, Cartesian product 0,2. So basically it is a rectangular, no? This is x and this is y. Interval. Okay, entonces my question is, as always, what kind of surface it is? What kind of surface it is? Because I want to have some idea how it look like this. Okay, this is my region in xy is given. My region is given is 3 and 2. 3 in x, 1, 2, 3, and 2, 1, 2. This is my region. This is my region, R. However, what kind of surface it is? Okay, put in red color. What kind? Plane, very well. It's a plane. Very well. The plane, well, the intersect is in 1 here. Okay, because x0, y0 is 1. It's a plane. I don't care. You want to see more clear, put in GeoGebra. It's a plane. So it's a plane, but I want to compare the surface area of the infinity plane. No, it's the plane that lie above this region. So when I projecting this, look, it's a piece of plane here. Okay, that part. Oh, no. Let me use another highlight. This piece of plane. So you don't need to have, in 3D, you don't need, in other problems, yes, but in the majority of problems, no. One accurate idea how it look like that. So I am doing always in 3D roughly sketch. Because I need to understand a little bit, no, but not too much. But I understand that the region is given. This is the region. It's given, region. In the projection onto XY plane. Okay? Those are using this formula, the explicit we are using. And the explicit, for example, you have already isolated Z. So you start always by the equation for the surface. In this case, totally explicit. Okay, because I know the formula, okay, this ds is the same as this. It's a square root fx squared plus fy squared plus 1 dx dy. Okay, and you compute that. You compute who is partial derivative f, who is f? Well, f is z. Always, well, not always, in this case. Entonces f en x es partial derivative. This expression with respect to x, que es 2. And partial derivative f with respect to y is 3. Okay, so now my equation now look like that. This is ds is equal to square root 4 plus 9 plus 1 dx dy. ds is equal to square root 14 dx dy. Now dx dy is, let me try to interpretation this. This is a elementary dx dy, elementary area dA on the xy plane. And I suppose I discovered using this formula que the elementary ds, que is here, this is ds, and this is dx dy. The relationship is square root 14 because, our plane has some inclination, okay, some slope. Therefore, the area of any element, it doesn't matter the dimension. When you're projecting onto the xy plane, the scale factor is radical 14. It's the relationship, the mathematical. It's the beauty of this, right? Now you are ready to set out the double integral? Of course you are ready. You are ready because now my surface integral is this. Now I change to the double integral. Where? In the region R. How is the region R? This is the region R. Look. This is the region R. Entonces super easy. The limit is clear. Es clear, es rectangular, entonces es super easy double integral. Entonces, what is my integrand function? My integrand function is this. Okay, look, we are doing now surface integral, que is not the same of the surface area. No, in the surface area, the integrand function is 1. No, in this case, no, 1 is x squared, y, and z. But we are in big trouble because in the double integral we never use z. We using always x and y. Ah, no, pero no, I know very well the relationship connecting C is no C. I replace by 1 plus 2x plus 3y. So you replace, and when you set out the double integral, and you make a decision, solving the problem using Cartesian, x and y, no plane, no polar, no, x, y. The only variable that participate in the game is x, y. And so you have z, because obviously this is 3D, you replace z by the corresponding relationship connecting c and x and y. And what about ds? Well, ds is clear, okay, radical 14, dx dy. And the limit, well, okay, the limit is easier. The limit of r is, for example, you integration first with respect to x. So I make a decision that order. I don't know why. So this order, dx first. So this integral is x from 0 to 3. And dy secondly is from 0 to 2. Boom. And the rest is algebra and calculable. And the answer is 171 radical 14. Entonces, what represents this? It's surface area, no? No. The interpretation this is not surface area because the integrand function is not 1. I don't know what is that. Suppose that this integrand function represents the density of this surface, no? Density function, okay, of this surface. Entonces this is number represent the mass of this lamina exactly in the yellow part. This is one possibility of the interpretation. Remember, the interpretation depending of the nature of the integral function. Any question? This is scalar, not vectorial. We start today studying vectorial. Pero no, one more example of the scalar. Easy. Suppose. Now, a little bit more interesting. Okay, suppose example 2 about the same idea, scalar surface integral. Compute what? Compute this surface integral. The integral function is 6xy ds, capital S. Remember, you need to be aware that we have ds capital and ds no capital. O small. It's capital, but it's small. This is R length. Entonces you apply this in line integral. But this is surface area. Of course, infinitesimal. And you apply this in surface integral. Okay, it's different, totally different concept. Some people call it different name to differentiate, but I suppose que not necessary. Okay. Entonces I need to, bueno, professor, okay, pero what is S? Bueno, S is the plane x plus y plus c equal 1. And the first octave. Okay, this is my surface. Okay, let me try to understand the surface. To understand the surface, I do the sketch in 3D. Why? Okay, this is a plane. It's obvious it's a plane. And it's obvious also that the intersecting is 1, 1, 1. No? So 1 here, and 1 here. This is my plane. Or at least this is my plane can lie in the first quadrant. This is 1. This point is 1, 0, 0. This is the point 0, 1, 0. And this is a point que es 0,0,1. Because you consider que two variables 0, la otra es 1. Entonces, this is my surface. Okay, nice. Let me try now to find ds. And the formula for ds is always the same. Suppose we use maybe explicit. So it's explicit, I make the using the explicit, you isolate the c is 1 minus x minus 1. The formula is square root fx squared fy squared plus 1 dx dy. Okay, so you need to transform a little bit this surface in one region, okay, the region lie on the xy plane. That is the reason I select that formula. I can do in another plane. Of course you can. You're projecting this in the xc plane, you change the formula, and you change the double integral. That's it. But I prefer xy when it's possible, no? Sometimes no. Okay, partial derivative. Well, partial derivative, okay, when you differentiate this expression, okay, the equation for the surface, que es the plane, when you compute the partial derivative with respect to x, es negative 1. And when you differentiate with respect to y, es negative 1 also. Ush. Entonces ds es igual square root negative 1 squared, que es 1, plus negative 1 squared, que es 1, and another extra 1 que we have, dx dy. And this is radical 3 dx dy. The interpretation is one elementary surface here ds have a corresponding and on the xy plane one flat, totally flat, horizontal dx dy. And the relationship between this area is radical 3 in this specific problem. Okay, ready. I am ready to set out the double integral. The double integral is equivalent to this surface integral. Put this together. And the region arc, I have no idea what is the region arc. Is 6xy. No C, nice. I like that. And radical 3 dx dy. Perfect. Okay, to see the region R, I can see this is 3D picture. I want to do a sketch in 2D. Well, si I assume que C is 0, entonces my equation is x plus y equal 1, and it's line. Of course, no line is a segment. No? It's a segment connecting this point, the point is 1, and this point is 1. This is the equation for this part. Entonces, when you set up, in order to compute the double integral, the limit, well, remember I prefer always integration in this direction, from 0 to something que corresponde to the y of this line, que is 1 minus x. And after you expand in this direction, exactly, we are doing double integral. No, it's from 0 to 1. Boom. The rest is piece okay for us. And the answer is radical 3. Radical 3 over 4, no? Radical 3 over 4, okay, so. Yeah, radical 3 over 4. Boom. End the story. Any question? Wow, easy. Surface integral, no big deal. No. It's big deal in my opinion. This is the most complicated part in calculus 3. Yeah, you have to put dx dy. Yeah, you can. I believe, yeah, of course. This is only double integral, and you solve it any way you want. You put the y here, dx and your integration in this direction. But I don't want to explain this because you know, right? This is the x0 and the x of the equation, que es 1 minus y, ¿no? Si you change. Entonces here is 1 minus 1, minus y, sorry. And after dx is from 0 to 1 again by coincidence. This is a double integral. This is a piece of cake. We passed this class, no? So chapter 3, we pass. I get good grade, no? Okay, another question, another important question. Come on. Do you follow me or you are totally lost? Surface integral. You don't understand surface integral? Okay. Sure? A ver, follow. Okay, Victoria. Okay. Okay, I promise in the review packet always happen. This is classical in the review packet. When you solving this, you have some foundation, elementary, so you see in detail. Always happen. This is the education. It's a process. Little by little. Now, I want to discussing, at least today, start doing the vector surface integral. Vector surface integral. Okay, what is the idea? Well, the idea is que now the integrand function is vector field. Oh, entonces what's the meaning of this vector surface integral? Maybe it's a flux in 3D. Okay, let me try to explain in detail this idea. Okay, look. Suppose we have surface like that. We have vector field like that. Remember, vector field is a bunch of vector, no? Entonces I do for vector, but you know, you have infinity vector, no? Entonces, what's my goal? Bueno, my goal is compute the flux, que es the amount, o sea, how much vector field passing through the surface S. This is the surface S, no? This is the surface S. This is the vector field F. Entonces, what is the quantity? What is the formula to compute? Easy. The formula is you compute the dot product using normal vector. Okay, normal vector. What is the normal vector? Well, normal vector is a normal vector here. Why no? Normal vector in opposite direction, no? Sometimes we said the majority of surface in the real life have two faces, no? Because you want to find the flux out the surface. Well, we're using one normal vector, no? So you want to compute the flux inside the surface, suppose que so. So we have two possibilities. Entonces now you select in the problem specification. Well, I need the unit vector outer the surface. So I use one. So you have two possibilities because the majority of the surface is orientable. I want to explain in detail this idea. But well, first of all, is, you know, the dot product F, dot product normal vector, in my opinion, measure how much something, vector field. Passing through the surface. Okay? And well, okay, this is the in one specific point. For example, this point. However, if you want to get the global idea, entonces you perform the surface integral using vector integral function. Wow, and this is my formula. One of my elementary formula. There are different formulas I want to study today. Okay, but I want to practice a little bit. Look. Well, in this case, what do you think about this integral in this specific figure, in this specific picture? What do you think about this? This is zero, this is positive, or this is negative? Under the supposition that this is the normal vector. This one. Point up. Point up. Opinion, guy. I launch a question. What do you think about the flux? Que es the surface integral of this formula and this specific number one problem. You suppose positive, zero, or negative? Es positive. Es obvio que es positive. Daniel dice es positive, professor, because the angle in between the any vector and the normal vector is acute. And the dot product is positive. Super. What do you think about in the example 2? In the example 2, I have the surface. I have this vector field. And what do you think about the flux passing through the surface? Well, suppose to understand much better, we have vector field below the surface, above the surface, but in this case, look like that. Normal vector, you know, always is like that. Or depending, no? I define we have two possibilities to define normal vector: up or down, no problem, or right to left. Think about what do you consider is the answer for number 2? I want to do number 3, another problem. Number 3, suppose que it's a balloon, it's a sphere, okay, and the vector field look like that. Boom. We have another, suppose this, number 4. Suppose it's one surface like that, and the vector field is like that. And suppose 5, one more. The same kind of surface. But in this case, the vector field is like that. Well, let me use the vector field and record. So what is the answer in number 2? Somebody get the answer. Only Gerardo. Come on, I want another participation. Come on, guy. Come on. Come on, Victoria. Come on, Heidi. Oh, Heidi, you are late. Too late. Leonardo, late. Shajir, late. Brandon Thomas. There are no reason to be late. We have no parking lot problem. We have no tire flat. We have no problem with the battery of the car. Only internet. Well, maybe. Okay, opinion, guy. David Restrepo. Robin, you are doing very well in your homework and your tests, like Ricardo. All clear. All clear. All clear. The answer is not all clear. Okay. Well, okay. What the answer I need is 0. Es 0 porque es 90 degrees. O sea, es perpendicular. O sea, the vector field F and the normal vector is 90 degrees. Entonces, the flux is 0. What do you think number 3? Well, professor, I don't understand very well number 3 because what is the normal vector? Well, normal vector is like that. Or like that. Si you suppose outer the surface, you suppose. Entonces, what do you think about the flux and this balloon? Es 0. Es 0 because sometimes it's, for example, in that part is in the same direction. O sea, es some flux. So some vector field go out the surface. Some vector field, the same amount, go inside the surface. And here in the top, in the bottom is 0 because it's 90 degrees. So it's 0 again. So the flux is 0 in this example. The flux is 0 in this example. The flux is positive in this example. Guys, it's important because I never understand what is the flux. Okay? Some teachers don't explain this. Some teachers put a formula, integration, blah, 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 blah. And what is, entonces I don't understand what is the flux. Entonces, en number 4 and number 5. What do you think about number 4 and number 5? Bueno, profesor, pero you don't specification the normal vector. You assume que it's always up. No. Okay, you need to specification. The normal vector, I suppose que es this direction. But in this case, no. I suppose que es in this direction. Because I need, in number 4, compute the flux out the surface. However, in the 5, I need to compute the flux inside. Get in the surface. So now, you need 2 pieces of information to determine the flux. We need the vector field, okay. But we need definition in what direction you consider que es the normal vector. What do you think about number 4? Positive or negative? Or 0? And number 4, come on, opinion, come on. I want participation, no Gerardo, another guy. Come on, Hadi, Leonardo, Shair, Brandon, come on, guy. This is the mute guy. You are sleeping. Come on, he present. A ver, Heidi, are you there? Bahau, are you there? Yes, say yes or no, or you're absent. Leonardo, are you there? I erase in the attendance. Okay, yes. Shajir, Brandon, Thomas. Ricardo says, yes, I am here. Okay. Ricardo, I know that you always are here. You are fantastic too. By the way, congratulations, Ricardo. Ricardo finished the test number 4 online. Es positive. Es obvio. Es obvio que es positive. Daniela. Es obvio que es positive. Y en number 5, Daniela. Robin. Davey. Carlos Duque. Okay, so you don't see negative. Negative. No, because it's in the same, I put intentionally to confuse you. Okay, it's in the same direction. Look, the dot product F that M is obvious que es positive in this. If the dot product F that N is obvious que es also positive because it's in the same direction. Yes or no? Do you forgot the dot product? Eh? Okay. And the rest of the time we have, okay, I want to disconnecting a little bit. So next time we compute the flux, so vector surface integral. I think F n cosine theta. Pero the interpretation, Girardo, the interpretation. When you have dot product, you have one vector like that, A, and one vector like that, B. A dot product B. ¿Es positive, es negative o es 0? It's positive because the angle is acute. So you have this situation, suppose B vector like that, and A vector like that, and the angle is obtuse. The dot product is negative. And when the 90 degree orthogonal, okay? No surprise. Okay, I want to discuss another important thing, theoretical, of course, que es orientable or non-orientable surface. O sea, orientable. So we have 2 kinds of surface. And you see in the flux chart, I saying last time, one question say, our surface is orientable surface or no? So the negation is obvious, it's non-orientable surface, no? Non-orientable surface. So the majority of surface that we can find, and the problem is orientable. What mean orientable? Okay, you have to face, coño. So you have to face, therefore you can define one unit vector in this direction or normal vector, sorry, or one normal vector in this direction. This is the majority, but there are surfaces that is not orientable. There are surfaces that have no two face. There are surfaces that have only one face. Do you believe that? Only one face. So we have two special. Two special that I bring today to illustrate. I bring some video on YouTube about the one guy gets called Mobius strip. T. That's one typical example of the non-orientable. And another case, the bottle, plain bottle. Plain bottle. You think it's very, very interesting? Enjoy this. Let me try to find, I prepare for you some video. Do you see the whiteboard now or no? You continue to see the whiteboard? Let me try to, now let me know if you don't see the YouTube when I open the video. This is how make the Mobius strip. Now you are familiar. And after you understand what is the reason that the Mobius strip have only one face. And this is the claim bottle. And do you understand what is the reason that the claim bottle have only one face? Okay, I click here. I open YouTube.
Grammarly does more than catch errors.
Okay, do you see the YouTube or no? I don't see. Okay, no problem. I understand. I suppose that. So I share that. Boom. Now you see, right? See now. Look. Wow. Do you see how you make a Mobius strip? Now I want to prove in another example. You know, one image is much better than 1,000 words. I can explain with the word. This is impossible. Let's do animation to understand what's the reason that this strip have only one face. Wait, I suppose that you don't see the YouTube again. Let me see. No. Okay. This is the problem. Okay, I need to share several times. Okay, now in this video you see what is the justification. Okay, the Mobius strip have only one face. Look, it's a ball, and the ball go in the edge of this, but you have only one edge. Two face, no one face. Do you see or no? Two side, two edge. In reality, only one side. Oh, amazing. Now the bottle is more amazing. Look at the bottle. The bottle, claim bottle. Claim bottle is something like that. Wow, weird. Bottle. Claim bottle. Let me see how you make claim bottle. Look. Okay, Skype. Okay, wait a second. What's going on? Okay, here, Skype. Okay, there you go. Let me share the screen for the YouTube again. Okay, here and here. Okay. You see how you make, but it is complicated. The claim bottle. Look. Good, very good. Do you see the claim bottle? Now in the next video, you see, very good, cool. Okay. In this video, you can see one ant walking inside the ant bottle, and the claim bottle have only one face, no two face. Okay, let me share the last video. Share last video. Okay, boom. Okay, look. This is a short video. Look, one ant walking around the claim bottle. Go inside. Oh, what's going on? Okay, now go to the other part. And go outside. This bottle have only one face. This is what's the most important conclusion, guys. The most important conclusion is that we have two kinds of surface, orientable and non-orientable. Yeah, of course. Again, the last video, no? Let me try. Wait a second. The last video. Wait a second here. Over there. Okay, look. Okay, now I stop the video. And also share this video here, over there. Okay, boom, dale. You see or no? Gerardo, yes or no? I repeat several times until you get the idea that the ant is moving. The ant start outside the bottle, and suddenly in one moment the ant go outside. Wow. Okay, repetition. Play it now. Look, repetition. I'm moving on onto the hole that we have at the bottom. I go inside. I'm moving around the tube. I go in opposite direction. No? Fantastic. Do you see Gerardo? Okay. This video you can find. I saw that. So basically, we have two kinds of surface: orientable and non-orientable. Fortunately, Super cool. Fortunately, the majority of the surface we're using to compute the flux is orientable. So you don't worry for this. This is just theoretical thing to illustrate that we have two kinds of surface. It's orientable or not orientable? No, it's orientable. Okay, now you can compute the flux. The next time